So for today, our topic is convex mirror, okay? So convex mirrors are in some ways harder. The ray tracing diagrams are a little bit weirder to think about, but in other ways, they're a lot easier because the image is always the same. It's always virtual, diminished, and erect, okay? So convex mirrors, sometimes called diverging mirrors, because rays that come in parallel get spread out. They diverge. So if we imagine a convex mirror, it's not in like a cave, it's not caved in, right? As these rays come in, they're going to follow the law of reflection. So reflect off the normal, okay, and get spread out. Okay, so these ones that come in get spread out. So again, just to see it, okay, convex, so it comes in, there's the normal, and it leaves the same angle relative to the normal. Just realizing now when I taught this in grade 8, okay, the dashes just meant reflected. That's not actually how they go. So now we can imagine, what would our eye see? Well, it would trace those rays back, and notice how they all seem to converge at a point behind the lens. Guess what? A focal point can be virtual, so to speak. It can be behind the lens, okay? So they appear to converge there. No rays are actually converging there, but these reflected rays all appear to converge there. So again, the image will always be diminished and virtual. It'll always appear behind there. So you know the ones at a gas station, okay, or in a parking garage or whatever, okay? Those security type mirrors are all convex mirrors, because the way that they spread out the light means you can see light from farther away. So you can actually get a better angle. For example, also your rear view mirrors on your car, those are convex mirrors so that you can see farther. But what does it always say? It always says images are larger than they appear, right? Because at the cost of seeing wider is that they appear smaller. We'll see why with our ray tracing, okay? You can try this for yourself. In fact, you can do concave and convex with a spoon. Okay, look at the back of a spoon. You will appear smaller, but you will appear virtual, and you will appear right side up. If you flip that spoon around so it's concave, you will appear upside down, okay, beyond the focal point. As you get closer and closer, it'll get bigger and bigger and bigger. You'll eventually see nothing, and then if you get really close, you'll be able to see yourself larger and erect. So don't forget our direction convention, okay? Because the mirror, if we were to imagine it as an actual sphere, an actual circle, right, with a center of curvature there, what did we say was going to be the negative side of it? Everything over here was going to be negative, okay? So the focal point is negative. Focal point is behind the reflective surface. Also for the center of curvature. So what does that mean? It means for convex mirrors, the focal length and the radius of curvature are both negative, okay? So that goes for when we put them into our mirror equations. Okay, so our rules for ray diagrams are actually the exact same. So we're still gonna follow that PFC. The only thing is they get a little trickier to think about what they mean, okay? So I'm gonna switch to paper again because I think it's better for you to see me do it actually with a ruler on paper than it is for me to just draw them up here where you can't tell what I'm doing. But you'll see the rules are the same, just the way we interpret them in the end, there's an extra little trick to it. Just like before, ones that are parallel to the principal axis, okay, will reflect off the mirror and be projected through the focal point. So now the only difference is that instead of actually passing through the focal point, they're just going to get projected through the focal point, like we saw before, okay? Like we saw on that PowerPoint. So parallel to the principal axis, okay? Then projected through the focal point. So I'm going to use a dashed line because this is not real. Now on that PowerPoint, the dashed line I was just using to mean reflected. Okay, that was because I was teaching grade 8. It was a little bit different. So that should be dashed because it's behind the mirror, right? That is not a real ray of light. However, this one is, so it should be solid. Okay, there we go. Rule 1. That's it. Now, light rays that shine toward the focal point will reflect parallel to the principal axis. Notice nothing different here. It's still, if it goes towards the focal point, it will reflect parallel to the principal axis. So that just means you have to do a little more thinking here, okay? So be careful. This one is tricks students up quite a bit sometimes, okay? Okay, so it comes in towards the focal point, but here it gets reflected. So it gets reflected parallel to the principal axis, which means if our eye is over here, what's the projection we see? Okay, well, we see this as the projection. It appears to us that the ray came from there. Okay, so slightly different there. We don't just go guns blazing through the focal point. We have to first reflect and then think about, okay, what does that reflection mean for where we see it to come from? Okay, for rule 3, this one honestly should maybe be your more go-to, okay? Before we use this one as the check. This one I would say almost use this one as your one of your 2 rules and then use that focal point one as a check. So light rays that shine towards the center of curvature will reflect back on themselves, okay? So if it's headed towards the center of curvature, it will come in and it will just reflect right back the way it came, which means if our eye's over here, what will we see? We'll see a ray of light that will come that way. Okay, so it'll come in and reflect right back the way it came. And when our eye sees it, it will think, huh, it looks like it came from over there, right? And again, rule 4, nothing too different here. Light that shines on the vertex will reflect off at an angle of reflection equal to the angle of incidence, which they all do, but this one just is a little bit easier to draw. Still, this one really just used as a check. It requires the most guesswork. So if it comes in and hits the vertex, okay, it will reflect, and again, I have to kind of estimate, reflect at an angle equal. Now, if our eye's over here, right, if our eye's over here, what do we see? Well, it says, huh, I see a ray, and it looks like it came from over here. So again, we can put all these rules together and start forming an image, okay? So we drew our parallel one that went through the focal point. Now let's draw our one that was headed to the focal point, but got reflected parallel. So headed to the focal point, but got reflected parallel to the principal axis, which means our eyes would think it came from over here, okay? And just like before, we can now already kind of predict that the image should be there. But let's go ahead and do another one just to check. I kind of switched those. You should actually probably do this one for convex mirrors first. But as you can see, okay, look at that. That's already looking pretty good. So it's going to come in. Yes, it's going to get reflected, but it's just going to go right back along the way it came. That's our center rule. So already we have 3 converging there. If we really want, we can do a double check with our vertex and see that. Angle of incidence equal to angle of reflection. Okay, and if we trace that ray back, yes, it's in the same neighborhood. In fact, it's kind of dead on, right? So feeling very good about the fact that our image must be forming here. And what did we say all convex mirrors do? They produce virtual, diminished, erect images, okay? Now I have, right, this was a concave mirror, but if I flip it over, it's a convex mirror. So notice always erect and I'm never upside down, okay? And I'm always smaller than I should be, right? I always appear to be, and I'm always smaller than I should be, right? If I put my hand there, you can really tell. That's not how big my hand should appear from that far away. That's only a few inches, but my hand looks way smaller. So not as interesting, even though the ray diagrams are actually a little bit more complicated because we're now dealing with virtual rays, okay? And if I take my, right, and we can see why they call it a diverging lens because it makes the rays diverge, right? But it's still just following the law of reflection. Because the angle of incidence is different, because the normal is different, because it's going like this, right? You get the angle of reflection being different as well, even though I'm still keeping the lines parallel. It causes parallel rays to diverge. Now, if you trace these rays back, notice they all kind of, if you look at my finger, right, there's kind of a pivot point back there where those would appear to come from. So there is a focal point. It's just behind the mirror now. And rays aren't actually focusing there. They just appear to focus there. Okay, so just so you can see it one more time, although the result is always the same for diverging diagrams, again, the ray diagrams do trip students up a little bit more. So I'm going to show you it one more time. Okay, feel free to skip past this if you already got it and you don't want to see it again. But realistically, Okay, so if we draw them really careful, it can give us our answers, but realistically, we're going to use the equations most of the time anyway, unless the question says draw a ray diagram, in which case you should. Okay, again, nothing changes because the focal point and the center of curvature are over here now. They're still, the focal point is still half of the center of curvature. So I'll go at 5, and I'll go at 10. All right, so an attendant sees a person filling up and then drives away without paying. The police ask for a description. The attendant knows the mirror is 15 meters away from where people stand to fill up. If the robber looked to be 80 centimeters tall and 10 meters away, how tall was the person? So definitely one that's more made for our equations, but let's go ahead and try it out. So this is going to be 15 meters. Sure, why not? And let's go ahead and draw our, I'm going to do P and C. That's really what you should stick with convex. The F1 becomes more of a check, mainly just because it's the one that trips students up more. Comes in parallel and gets projected to the focal point, because that's what the focal point does. Converges rays or makes them appear to converge. So dotted to show that it's behind the mirror. It's not a real ray of light. Okay, and then, like we said, probably better to use the center for diverging mirrors or convex mirrors because it's just a little harder to mess up. So it would come in, it would get right back reflected the way it came, which would make it appear as if it came from over here. Okay, so look at that. We already have 2 rays crossing, and just like we should, okay, they appears to be erect, diminished, and virtual. Let's try our focal point 1, because again, that's the hardest one, so maybe that's the one you should see the most. Okay, so it's going to go to the focal point, it's going to go to the focal point, but it gets reflected parallel to the principal axis. And so when our eye sees that, which is over here, it says, looks like that ray came from here. Okay, and there we go. That's pretty good, right? That definitely looks like, so there's our image. So just like we would expect, virtual, diminished, and erect. Now, we already knew that, so let's get the math to actually tell us our answers. Okay, so let's actually read this in a little more depth. The attendant knows that the mirror is 15 meters away from where people fill to stand up. Okay, so it's 15 meters away from where people stand to fill up. So in other words, the object that was reflected to her, this gas thief, right? The object was 15 meters away from the mirror. So that is DO, okay? If the robber looked to be 80 centimeters tall, that is HI, right? And 10 meters away, so they appeared to be 10 meters away, that's DI. How tall was the person? So we're looking for how tall was the person, so HO is what we need. So if you look on your data sheet, we got a DO, a DI, an HI, and an HO. You'll notice that we have the equation. Well, we have M equals HI over HO equals negative DI over DO, right? So we can actually solve this without ever finding M. So we want HO, so let's just get it out of the denominator. Or if you want, you could flip both sides. So HI equals negative DI over DO times HO. And then I'm just going to go ahead and multiply by this reciprocal so that they both cancel. You know what I mean? So times, I'll do the negative even so I can get rid of that. Times negative, if I want DO to cancel, I put it on top. And if I want DI to cancel, I put it on bottom. See what I mean? Now I have DO over DO, DI over DI, and negative. So just have to multiply this side by negative DO over DI as well. And we have that. The height of the object, the height of this gas thief is equal to negative HI DO over DI. Once I multiply that out, and now we just plug in. Okay, now we need to be really careful about negatives here. I probably should have mentioned this at the beginning, okay? The robber looked to be 80 centimeters tall and 10 meters away. But is DI 10 meters? Do they appear to be in front of the mirror? Or do they appear to be behind the mirror? Well, it's a convex mirror, right? So they appear to be behind it. Okay, so DI is actually negative 10 meters, right? Our ray diagram can confirm. That is the negative side of the mirror, okay? So just mentioning that now before I go in. Okay, so HO equals negative. Now, you're probably getting a little bit of anxiety as a physics student about centimeters and meters getting mixed here, okay? And you should, good. That's well, don't want you to have anxiety, but it's good that your gut reaction is I shouldn't mix units. Okay. If you wanted to convert, that would be fine so that they were all in meters or all in centimeters. I'm just going to show you it would work out okay here. But if you're going to do something like this, you better be canceling your units to check out that it's actually okay. Okay. So HO equals negative HI, and HI is 80 centimeters. Okay. Times the distance of the object. So that is on the real side of the mirror, right? This is DO, and that is 15 meters. Divided by the DI, and be very careful, it's not 10 meters, it's negative 10 meters. And so do you see what I mean here, right? You better not be mixing units unless you're checking that it's fine. But it is fine here because we have meters over meters, so all that means is our answer will now be in centimeters. We could have converted everything to meters and gotten our answer in meters. There would have been nothing wrong with that either, okay? So I got, when I did it, the negatives cancel, which is good. You should never get a negative HO or DO because we define those as the positive direction, however the object is oriented. But I got 120 centimeters, okay, which honestly, I'm going to go ahead and convert that anyway, so that was kind of for nothing. 1.2 meters. Instead of using scientific notation, I'm just going to do that. So that is how tall the person really was. So theory questions are still kind of safe, right? So like I said, memorizing, don't purely just memorize, be able to reproduce stuff, but it wouldn't hurt you to kind of think about the images formed by different types of mirrors, okay? Luckily for us, convex is fairly straightforward because it's always the same. So let's just go through these one at a time and see if we can eliminate until we've eliminated all but one. So a convex mirror produces virtual images, yeah, that are upright, yeah, and smaller than the object, yep. Only when the object is placed beyond the radius of curvature. Boo, no, right? You can't, how do you get an object beyond the radius of curvature for a convex mirror? You can't, that's behind the mirror. Okay, a convex mirror always produces virtual images, yep, that are inverted. Boo, they're right side up. Okay, when you walk in a gas station, you don't look upside down in the mirror. Okay, smaller than the object though, that's true. Okay, a convex mirror always produces virtual images, that are upright, and bigger than the object, boo. Objects in mirror are smaller than they appear, right? That's what your rear view mirrors say on your car. Well, so it looks like it's going to be D, but let's double check. A convex mirror always produces virtual images, that are upright, yep, and smaller than the object. Very good. Okay. When you're thinking about convex, think about your rear view mirrors in your car, right? The world doesn't look upside down in them, but it does look smaller. Okay, when a girl who is 122 centimeters tall, so what variable is that? Well, that's the height of our actual object, okay? Stands 40 centimeters in front of a particular mirror. So she's 40 centimeters from the mirror. That is the distance of the object. Her virtual image in the mirror is upright. Okay, so HI is positive and 54 centimeters tall. So that's HI, okay? By the way, her virtual image, that means DI is negative because it's forming behind the mirror. Okay, so this actually does require us to kind of just rely on memory. We could draw them out, okay? We could draw them out and get all the ray diagrams, but realistically, this one becomes a lot easier by knowing some stuff, okay? So if it is convex, what do we know? It will always be, the image will always be virtual, upright, erect, and diminished. So is it virtual? Yeah, the question even said that, right? The negative DI, it's virtual. Is it erect? Yeah, it's upright, okay. Is it diminished? Well, she is 122 centimeters tall and the mirror is making her look 54 centimeters tall. So you bet, it's diminished. Okay, should we jump right to this being a convex mirror? Well, we should think about concave mirrors, but if you think about them, you will realize that, okay, the only time a concave mirror produces a virtual image, it also makes it larger. So it can't make virtual and diminished. It can only make virtual and enlarged. That's when you're within the focal point. Beyond the focal point, it's always real. It's only ever virtual within the focal point, and then it is enlarged, not diminished. So it is not going to be concave. It is going to be convex, but to figure out where the girl's image is, we're going to need to use some math. HI over HO equals negative DI over DO. So what are we looking for? We're trying to figure out where her image actually forms, right? The image. Where is the image relative to the mirror? So let's go ahead and multiply both sides by, you okay if I do negative DO? I don't know why I'm asking you like you're here. Okay, so negative HIDO over HO equals DI. So DI equals negative. H image was upright, right? So it was upright. So should it be positive or negative? Well, we already said it should be positive. So DI equals negative 54 centimeters. DO is always positive, right? We define the object's orientation as the positive kind of orientation. So 40 centimeters divided by the height of the object. So she is 122 centimeters. And then again, by default, that's positive. And so centimeters, centimeters, our answer is going to be in centimeters. Nothing wrong with that. Our DI is negative 18 centimeters. Good. We wanted a negative DI, right? Because it was virtual. So that's good. We wanted a negative. It's just saying here, though, how far is it from the mirror? So it's asking for a distance, not a displacement, right? So convex and 18 centimeters. Okay, big thing that honestly didn't come up much in these examples, folks. Okay, be careful when you go to do the practice or the summative. The focal length is negative. So when you go to use this guy for a convex mirror, okay, just don't forget F will be negative because it's behind the mirror. So if you're looking for practice with this, check what the agenda or Google Classroom says for topic 2 practice questions.